All right. So we have said that the Poisson random variable is a limiting case of the binomial random variable. Remember now, in binomial random variable, when the size parameter is too large, size parameter n is too large, and at the same time, if the success probability is very, very small, in that case, we can say that the probability mass function of the binomial random variable converges to the probability mass function of a Poisson random variable, and the rate parameter of this Poisson random variable will be equal to n times p, the size parameter of the binomial random variable times the success probability. Now, in that sense, a Poisson random variable is practically much more observable in real life compared to the binomial random variable. So following two examples are going to indicate that we can apply a Poisson approximation to the binomial random variables, where we have a very large size parameter and a small success probability. Now check the question. The probability that a person dies from a certain respiratory infection is 0.002. The question says that find the probability that fewer than 5 of the next 2,000 infected person will die. Now, here in this question, the success we are talking about is unfortunately death. And there are 2,000 experiments. There are 2,000 people who have a respiratory infection. And for a person to die to this respiratory infection is a very small probability, 0.002. So here the number of experiments that we are going to perform or observe is a very large number, 2,000, whereas the success probability of an experiment, which is the probability of death, is 0.02. And the question is asking us the probability of the number of successes to be less than 5. So this means this variable, number of people who dies due to the respiratory infection, can be modeled with a binomial variable, where the size parameter is equal to 2,000, and we assume independence between the survival status of these patients. And the success probability for each person is 0.02. So x is a binomial random variable, and the question is asking the probability of x being less than 5. The number of people, number of patients that die being less than 5. So this means what? We are going to sum up the probability mass values for integers from 0 to 4, and the probability mass values will be calculated by the probability mass function of the binomial distribution. So here we have the size parameter n equal to 2,000 and the success probability equal to 2 over 1,000. And even though there are only 5 probabilities that we are going to compute, this part especially, we have a very, very large probability, but the power here is going to be quite large as well, is going to make things complicated, and it will consume so much time to calculation by manual methods. So we need a computer to calculate such a probability, and by the means of a computer, this 5 probabilities for values from 0 to 4 will sum up to 0.6288, okay? But remember, it is going to be quite complex to calculate by hand. Now, in this question, as you can realize, the size parameter is very large, whereas the success probability is very small. So in that case, we can approximate this binomial random variable with a Poisson random variable. Remember now, for using such an approximation, we need to satisfy both conditions. N must be very large, the size parameter must be very large, and the success probability must be very small. So we say that if we are going to approximate this binomial random variable with a Poisson random variable, the rate parameter lambda should be equal to n times p, in this case, 2000 times 0.002, the rate parameter is going to be equal to 4. Remember now, NP is the expected value of the binomial random variable, and lambda, the rate parameter of the Poisson random variable, is also the expected value of the Poisson random variable. Now, under the assumption of Poisson random variable, the probability of x being less than 5 is going to be calculated by summing up the probability mass values from 0 to 4 under the probability mass function of a Poisson random variable. The rate parameter will be assigned as 4, and by plugging in values from 0 to 4 to this probability mass function, we are going to calculate the approximate probability of the number of patients dying due to this infection being less than 5. Now, this part is dependent on x, and this part is a common multiplier in every term in the summation, so it can get out here as 0.0183. And the remaining part is going to be calculated with a much more simpler manner, and the summation will be 0.6288. So you see, we get exactly the same probability up to 4 digits. So this approximation here works pretty well. So instead of using a binomial random variable to model this value, the number of people dying due to the respiratory infection, we can use another approximation, which is a Poisson approximation, and up to 4 digits after the decimal, we get exactly the same probability. So in this case, the approximation works perfectly. Now we are going to solve another question, but in this question, the approximation may not work perfectly. See, we have to crack a password which contains 120 digits, each of which might independently contain characters from Turkish alphabet from A to Z, or a blank space with equal chances. So this means in order to develop a password, for each digit, you have to choose one of the 30 characters, because there are 29 letters in Turkish alphabet and there is one blank space. So potentially you can write any of the characters out of 30 in any of the digits. Whenever we try a random password, the user interface returns the amount of digits that are guessed correctly. So this means what? Whenever you write a random password, it is going to, the computer is going to count the number of digits that you have guessed correctly, and the interface will give you this value. And we let the number of correctly guessed digits, or the number that we observe in the interface, it is going to be denoted by capital X. Obviously, this capital X is going to be a random variable, because every time you randomly guess the password, the number of correctly guessed digits is going to be different. In the worst case, you can guess none of them. And in the best case, with a very, very small probability, you can guess all of them. So what type of random variable is X? So whenever we randomly guess the password, we are basically repeating a Bernoulli experiment 120 times independently, and in each of these repetitions, there is the chance of being successful of 1 over 30, because you can guess a letter correctly, a digit correctly, with 1 over 30 probability. So we say that the random variable X is binomially distributed, where the size parameter is 120 and the success probability is 1 over 30. And part B tells us what type of random variable can X be approximated to. Obviously, the one thing that we have learned so far is approximating binomial random variable with Poisson random variable. However, using such approximation can be a correct approach under 2 conditions. The size parameter must be very large and the success probability must be very small. So let's check. The size parameter is 120. It is not very, very large, but it is large. And the success probability is 1 over 30. Again, it is not quite small, but it's small. So we can approximate the binomial random variable here with a Poisson random variable. However, would it be a good approximation? We'll see when we calculate the results. And for part C, it says, why can we do such an approximation? As we have explained, we can approximate a binomial random variable with a Poisson random variable when the size parameter is sufficiently large and the success probability is sufficiently small. So both conditions, remember now, both conditions must be satisfied to do such an approximation. What is the probability of x being less than or equal to 2 under the approximate distribution? So under the Poisson assumption, what is the probability of the number of digits guessed correctly being less than or equal to 2, or at most 2? And for part E and F, we are being asked the expected value and the variance of the number of digits that are guessed correctly under the approximate distribution, under the Poisson assumption. And for part G, we are being asked the true variance x. So we are going to go back to the binomial assumption, the true assumption. And under the binomial assumption, what is variance x? We are going to calculate. Now, here are the answers. So the number of digits that are guessed correctly whenever we randomly try a password is a binomial random variable where the size parameter is 120. There are 120 Bernoulli trials which are independent from each other. And the success probability is 1/30 for each of these Bernoulli trials. And Poisson random variable can be used as an approximation for this binomial random variable if we calculate the rate parameter as equal to n times p. In this case, it is going to be equal to 4. We can do such an approximation because n is large and p is small enough. But is this a good approximation? We'll check it. Now, for part T, under the Poisson approximation, what was the probability of the number of digits being guessed correctly to be at most 2? And we are going to use the Poisson probability mass function under the rate parameter lambda being equal to 4. And we are going to calculate 3 probabilities, x being equal to 0, 1, and 2. And when we plug in these values, we get 0.2381 as the probability. And the expected value and the variance under the Poisson approximation will be equal to lambda parameter. Remember now, for Poisson random variable with rate parameter lambda, both the expected value and the variance is equal to lambda, that is equal to 4 in this question. However, under the true assumption, under the binomial assumption, the variance is formulated as n times p times 1 minus p. And when we plug in these values, n is 120, the size parameter, this is the success probability, and this is the failure probability. And the multiplication here will give you a 3.8668. So under the approximate distribution, the variance was 4, but under the true distribution, the variance was 3.86. So there is almost a significant difference between these variance values. So is this a good approximation? You can try by using a calculator or computer to calculate this probability under the binomial distribution. So instead of using the probability mass function values of Poisson random variable here, you can use the probability mass values for binomial random variable with this parameter setting and calculate this probability to see the difference. Then we can decide if this approximation is good or bad. However, the condition that makes this approximation a good approximation is to have a sufficiently large size parameter for binomial random variable, and at the same time, the success probability must be very small.